Hello and welcome to section 2.4 complex numbers. In this video we are going to be talking about imaginary numbers and whatnot. So remember, if you have any questions on any of these videos or any of these examples that we go through, please write them down and bring them to class so that we can talk about them. We'll have time to do that. So first thing is we're going to talk about reminding you what the complex number is. It's when we try to take the square root of -1 or what an imaginary number is, and when we take the square root of -1 we get I. A complex number is the combination of a real number, A, and an imaginary number like BI, and when you add or subtract those together you get a complex number. So that's just a quick little reminder of what's going on, and so now we're going to add or subtract our complex numbers together. Well, when you look at these, this is just like treat I like a variable when we're adding them together. So we could just add these guys together. So combining my like terms, I'm going to say 3 plus 2 minus I plus 3I, just writing them, regrouping them more or less, just kind of wrote them in a regrouping form. And then when I combine these guys, I end up with, and probably I shouldn't use parentheses, I'm going to get rid of that. And so I have 3 plus 2 minus I plus 3I. And so when I combine my like terms, I get 5 minus plus 2I, and that is the best I'm going to get for this addition. Over here, I've got a whole bunch of square roots and negatives and stuff like that, so I'm taking the square root of -4, which could actually be written as 2I when I simplify it. We want to simplify these as much as we can. We have plus -4, and over here we're subtracting a square root of -4, which means that I'm subtracting 2I. So when I simplify this, because remember we're dealing with the square root for -4 is -1 times 4, which could be written as the square root of -1 times the square root of 4, and when we do that, remember the square root of -1 is I, and the square root of 4 is 2, and we just write the 2 in front of the I. And so that's where these two i's came from. So you'll notice I have a -2I and a +2I, which will cancel each other out, or like terms. So the only thing I'm left with is a -4 as my solution. When I add these guys together, well, again, I'm going to get my like terms together. Be very careful. There's a negative signs outside the parentheses, so that negative sign is like -1 times each term inside the parenthesis. So when I get rid of the parentheses here, I'm going to say 3 plus 2 minus 3I. I just distributed my negative. And here I'm going to do the same thing. It's going to be plus 5 minus I. So now I just combine my like terms. So I've got 3 plus 2 plus 5, which is 10, and then -3I minus I is -4I. So that would be my solution to that problem. And so the next one, then, if I do this, when I add these together, again, here's that negative sign, so I got to be careful of that. I'm going to distribute to both of them. So since there's nothing really happening to this parentheses, I can just drop it. There's nothing, a positive sign doesn't do anything inside the parentheses, so I'm going to drop that parenthesis. And the last one, I'm going to distribute my negative, multiply it by 7, and multiply it by I, so I get something that looks like this. And so when I combine my like terms in this case, you'll notice that I have 3 plus 4 minus 7, so I end up with 7 minus 7, and then I have 2I plus 2I minus another 2I, so you'll notice that everything's going to cancel each other out, so you should get a solution of 0. There's our first example of adding and subtracting them together. Then we're going to talk about multiplying them together, and in this case we need to kind of keep track of what happens when we multiply i's together, and this will be taken care of also in class. So if we take I to the first power, if we take I times 1, we get I. If we take I times I, which is really I squared, we get -1. If we take I cubed, or I times, which is I times I times I, we end up with -I. And then if it's I to the 4th, which is 4 i's multiplied together, we end up with +1. And then the pattern will repeat itself for 5, 6, 7, 8, and so on. And we'll talk more about this in class. But I just needed to mention that, so when I multiply these guys together, I take 2 times 4, so it's really 2 times 4 times I, because remember, multiplication, we can multiply in any order we want as long as there's no addition or subtraction. So in this case, I'm left with 8 times I squared, and since we just said that I squared, I times I is -1, my final answer for this one is -8. And so then the next one, well, and this one's a little bit more of a challenge because we have addition or subtraction. And as soon as you have two terms being multiplied together, that's addition or subtraction, you have to either use the box method or FOIL or whatever, however you multiply binomials together. And so I'm going to multiply 2 times 4, which is 8. I'm going to take 2 times 3i, which would be 6i. I'm going to take negative I times 4, I'm using FOIL, negative 4i, and then I'm going to take negative I times 3i, which will give me negative 3i squared. And so now I'm going to combine like terms as best I can. I've got 8, and then 6i minus 4i is 2i's, and then down here I've got negative 3 times I squared, which happens to be negative 1. So I'm going to rewrite the I squared as negative 1. Combining these guys together, multiplying them together, it looks like I get a positive 3. So that positive 3 will get added to the 8. And so, because it turns into a positive, so 8 plus 3 is 11. So my final answer for this one is 11 plus 2i. That's what I'm looking for my solution on that one. The next one, when I multiply these together, well, I'm going to do the distributive property, and you may notice if you've been paying attention that this is just like a difference of two squares. So there's not really a shortcut to this, but it'll end up doing the same thing like a difference of two squares would. But I'm going to go ahead and FOIL this together. So I'm going to take my first terms, which is 9, 3 times 3. Then 3 times negative 2i is negative 6i. Then positive 2i times 3 is positive 6i, and then 2i times negative 2i is a negative 4i squared. Well, with this, you'll notice that the negative 6i and the positive 6i cancel out, so I'm really left with 9 minus 4i squared, and remember I squared is really negative 1. So to complete this, if I multiply negative 1 times 4, I get 9 plus 4, which gives me an answer of 13 for this one. And then finally, the next one that I've got here, I'm going to take 4i times both of my terms, so I just distribute. And so 4i times negative 1 is negative 4i, and 4i times 5i would be 20i squared. Well, remember, I squared is negative 1, so to rewrite this, I could write it as 4i minus 20, which is negative 1 times the 20, or I could write it as negative 20 minus 4i, which is more standard for our complex numbers. But either one of these guys is an okay answer for our solution. So moving along into the next one, complex conjugates, which actually this fits really nice to what we were doing before, that the complex conjugates will help us get rid of i's, just like when we try to get rid of rationalized square roots, we don't like having i's on the bottom of problems, so we use the conjugate. And this is, if you want to see a good example of the conjugate, go back to example 2 or example C. This has the conjugate. These are the conjugates being multiplied together, and you can see it works out kind of nice because we ended up with a whole number for when we multiplied our conjugates together. So that's really what we're talking about. And so our pattern for our conjugates is if it's a positive between the real number and the imaginary number, we switch it to a negative. If it's a negative between the real number and the imaginary number, it turns to positive. No matter what the sign is out front of the a, it doesn't really matter. So they're saying multiply this by its conjugate. So the original term is 3 minus 5i. So the conjugate will be, and I'll do this one in blue, is 3 plus 5i. And so the conjugate ends up giving us like a difference of two squares, which makes things very nice. So again, I'm going to go ahead and do this with FOIL just to multiply them together. But maybe you'll see a pattern, and you could maybe devise a shortcut from this. So if I take 3 times 3, I get 9. 3 times 5i, I get positive 15i. Negative 5i times 3 is negative 15i, and then negative 5 times 5i is minus 25i squared. So that's what I get when I deal with this, and I'm going to kind of move over here just because I'm running out of room. You'll notice the 15i's cancel each other out, so I'm left with 9 minus 25 times I squared. Well, I squared we just said was negative 1, so it's really 9 times 9 plus 25, which would give me 34 for the solution. And you can see, again, when we multiply conjugates of the complex number, we always end up with a whole number. And if you don't remember, go back to example 2, part C, and you'll see this. So we want to write this quotient in standard form. So we're not going to go ahead and divide this. We're going to multiply by the conjugate of the denominator. And so 4 minus 2i. So our conjugate that we're going to multiply by is change the sign between the real number and the complex number, which is 4 plus 2i. And so I'm going to multiply the top and bottom. And the reason we multiply the top and bottom by this is that if I was to put a fraction bar between these guys, this is a really the same number top and bottom. They're really ugly same numbers top and bottom, but they are the same number. So really, I'm multiplying this fraction, the original fraction, by a very ugly 1. But I'm not so that doesn't change the problem any. So when I multiply by this 1, then I still have to do all the stuff I did before. I have to use FOIL or the box method or whatever to multiply these together, but I'm not changing the problem. I'm just going to change the look of the problem. So by doing this, okay, I'm going to multiply my first term times both of these guys, which means I'm going to get 16. Oh, well, I should probably do this over here. So this thing's going to be equal to, so 16 on the bottom, and then plus 8i, and then I get minus 8i, and then it looks like a negative 4i squared. So there's the denominator of the problem. And then the top, I'm going to multiply, do the same thing. I'm going to take 2 times both of these terms. So I get 8 plus 4i. And then I'm going to take 3i times both of these terms, which gives me 12i. And it looks like 6i squared. Well, the good news is, on the bottom of this, that our conjugate simplification will help us out, and so the 8i's cancel out, so I'm left with really 16 minus 4 times negative 1, because the I squared turns to negative 1. On top, the best I can do is 8 plus 16i plus 6 times negative 1, because the I squared again is negative 1. So I can do a little bit of simplification to get my final answer. 8 and negative 6 will give me 2 plus 16i. That's the best I can do on top. And on the bottom, I really have 16 plus 4, which gives me 20. Well, you'll notice that the 2 and the 16 have a 2 in common with the 20, so I can reduce this all by 2 to get my final answer of 1 plus 8i all over 10. And so either one of these guys, probably on a test, the top one would probably lose you a point, but at least you got to the right spot. And the bottom one would be fully reduced to what we want as our solution. And so we have one more example of we're talking about graphing these guys in the complex plane. And so basically, the real numbers go along the x. There's our a value. And the imaginary are now our y value, which is the b value. So that's really all we're talking about. And so in this case, if I'm going to plot, I'll make this one, I'll put a box around it. That's the color I'm going to graph that one in. And so I'm going to count over 2 and up 3, because this is the BI plane. And so the point for this one is that one right there. And so then if I wanted to graph the next one, I'll make the next one in blue. And so if you notice, it says we're going back 1 in the real plane, and in the imaginary plane we're going up 2. So that would be part B. So let's go back. This was problem A, this was problem B, and then problem C is negative 3i, which I will put in red. Since we're not moving anywhere in the real plane, there's no real number to it, we're just going to go down 3 in the imaginary plane, and that's C, and that's the point we're talking about for that one. So that's graphing in the imaginary plane, in the complex plane. So if you remember, if you have any questions on this stuff, please come to class prepared to ask them, and I look forward to seeing you guys in class.